Hi everyone, this is from Modoka Blessings, and today I want us to look at the basics of chemical or acid-base equilibria. So in this particular text and this particular kind of topic, we get to examine how different kind of chemical reactions appear and how the dissociations of certain acids and bases really appear in the rate of a chemical reaction. So for example, today we've been given this question that says, we found that the equilibrium concentration of H plus in a 1.0 molar HF solution is 2.7 times 10 to the power negative 2 molar, and the percent dissociation of HF is 2.7%. Then that telling us to find calculate the concentrations of H plus and the percent dissociation of HF in a solution containing 1.0 molar HF. So one thing that we need to understand from this question is that we have been given an acid, and this acid is going to completely dissociate and give us its basic components. So for example, we've been given this acid as HF. So you know that this HF, once it completely dissociates, okay, and we know that this kind of a reaction is at equilibrium, okay, meaning that whatever we can have on the side of the product can come back on the side of the reactants and vice versa, okay. So now, once you have such kind of equation like this, you have the basic components, of course. You have the H plus, then you also have the fluorine ion. So you have the hydrogen ion, you also have the fluorine ion. And one thing that you need to understand from this question is that we are having the reactants here, and we're also having the products. And the Ka value for the expression that we're going to derive from this particular chemical reaction is Ka being equal to the concentrations of the products. Okay, the concentrations of the products we're talking about here are for the hydroxide ion, then multiplied by the concentrations of the fluorine ion, okay, or the fluoride ion, and then that's just fluorine, so that's just the fluorine ion, divide the concentrations of HF. Now I should point out something very important here. There are states, okay, chemical states of every single component that is given a chemical reaction. For example, this is aqueous, all right, and this is also aqueous. This is also equally aqueous. So you can only come up with an expression involving the terms or the basic components that we're having in this equation in this way only when they're appearing in aqueous form. If this was in liquid, we wouldn't have included as part of the expression. So what we simply have here is this is the expression. Now you should know that the Ka value is the acid dissociation value, which has been given as 7.2 watt. It's been given as 7.2 times 10 to the power negative 4. So that value has been given like that. So they're telling us to find what, calculate what this is. We want to find out what is the concentration of the hydroxide that is right there. Now you should know that when this chemical reaction was starting, we had the initial concentrations of this chemical reaction of its basic components, meaning that before it reached a point called we call equilibrium, the values of the concentrations of HF, the fluoride ion, as well as the hydroxide, as well as the hydrogen ions, were different from the values that we are going to have when this reaction reaches at the point of equilibrium. So now let's examine what we're talking about here. So now, I think many of us here have heard of what we call the ice table, where you have the initial concentrations before the reaction reaches equilibrium, and then you have the concentrations of the reaction after it reaches equilibrium. So now, I'll move a bit up here, meaning that I'm going to state them out. Given such kind of questions, this is what you should examine. So, what we have here are called initial concentrations. Okay, so these are initial concentrations, and then what you're going to have on the other side are called equilibrium concentrations after the reaction reaches at the point of equilibrium. These are called equilibrium concentrations. So now what do you do at this point? So what are we having? Initially, before this reaction started, we were given the concentration of HF, right? That is it. And then we were also given the concentration of the fluoride ion. Then we were also given the concentrations of the hydrogen ions. This is what we're examining. All right. So this was initially. I will put that to indicate this is initial, and then this is initial. And then what we're going to have on the other side after the reaction reaches equilibrium, what are we going to have? What will be the concentrations of that? On the other side, we're also going to maintain the fluorine after it reaches equilibrium. On the other side, we're also going to maintain the concentration of the hydrogen ions. So I want you to notice something very important in this particular text. Our main reaction at this point is this reaction here. We have these as my reactants, and I have on the other side as my products. We should know that when you're producing what we're calling the products, the reactants do what? They diminish. Okay? When you're producing what we call the reactants, we are producing what we're calling the products, the reactants here will do what? Will diminish. Okay? So since when you go back to the question that has been given, the initial concentrations of the HF that we had in this reaction was 10.0 molar. Okay? This 10.0 molar was the one that was dissolved in HF. The fluorine ion, when you get back to the question, it was given as 1.0 molar. But how was it given as 1.0 molar? Let me take you a bit back to the question. We were told that we were having here, we were given 1.0 molar NF. So this 1.0 molar NF is something of this nature. When this completely dissociates, you're going to have the mm, uh, the, the 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 sodium ions. Okay, you're also going to have the fluorine ions. So now the concentration of the sodium fluoride was given as 1.0, and if this completely dissociates in a chemical reaction, the concentrations of the sodium will equally be 1.0, and the concentrations of fluorine will equally be 1.0. So throughout the rate of this reaction, what we have here is 1.0 there for the sodium fluoride, 1.0 there for the sodium ion, and also 1.0 for the fluorine ion. So this gets to work for any strong bases and strong acids. I'll repeat that: strong acids and strong bases completely dissociate, and their concentrations are equal starting from what we had on the side of the reactants. So now we move on. We now know where the values of NF came from. So we have NF here as 1.0. On the other side, we have the value of the initial concentrations of the hydrogen ions here. What were they? It was a zero. Okay? Before the reaction reached equilibrium, we didn't have anything. Now, I want us to understand something here. There's a value we call the value of X. So this value of X is what is going to determine what we're going to have on the side of uh, a point when this entire reaction reaches what we call equilibrium. So what is this value of X, which is in form of mole per liter? Mole per liter meaning we're dealing with concentrations. So we want to find out the exact value of X had to remove the initial concentrations of these components of the reaction to a state of equilibrium. What were these values? So now the value of X basically comes from the balance in mole ratios of the reactants. So you can see that from the side of the reactants completely diminish. All right, they diminish to give us the products. So meaning that what we have here is just a mole ratio of 1, mole ratio of 1, and a mole ratio of 1. To say if what we're going to have on the other side is what? So meaning that for the hydrogen fluoride, which is on the side of the reactants, okay, it is not on the side of the products. We have the hydrogen fluoride on the side of the reactants. We have it as HF. So now because the reactants completely diminish, we should expect a loss in its concentrations. So what we're simply going to have here is the 1.0 molar we have initially minus the value of X that we don't know. And this value of X is dependent on the mole ratio of the A of the HF. And the mole ratio here is, the balancing mole ratio is a 1. If this was a 2, this would have been 2x. If this was a 3, this would have been E minus 3x. The fluorine ion. The fluorine ion, there's a balancing mole ratio of 1. And what were the initial concentrations? We still have 1.0. So this becomes 1.0. Now, because we have them on the side of the products, remember, we're diminishing the reactants to form the product. So on the products, what we're simply going to do is add this X because we're forming the product. Then we're diminishing the reactants. So that is a minus X from the HF, which is on the side of the reactants, and a plus X for the side which is on the side of the products. Because we're getting to diminish the reactants, then we're producing the products, so we're getting more of the products as opposed to the reactants. So just understand that concept. Then the initial concentrations of the hydrogen ions were zero, meaning what we're going to have on the side of the product is simply going to be X. Okay, this is just going to be 0 plus X. Okay, so X plus 0, you just know that the value we're going to get there is X, so we still just maintain the same thing. And there we go. So now we're going to derive an expression based on the equilibrium concentrations. So now let's find out what that is going to be. So now we know that this is the reactant and these are the two products. The Ka value is what? We said the Ka value initially after deriving that was equal to the concentration of the H plus ion, the F ions, which were the products, divide the reactants, which is HF. And then what we're going to do here is you're going to come up there. Then there's Ka. Ka is going to be equal to what? What were the products after the reaction reached equilibrium? The product of Hx is X. Okay, let me use a different color. You see, this is X. Then F. F is 1.0 plus C X. Then you divide the HF, the value is 1.0 minus C X. That is the concentration that we're having down there. So now this value of Ka was given, and the value of 7.2 times 10 to the power negative 4 molar. And there you go. You have it like that. So basically, one thing I want us to understand from here is that this value of X we're talking about is a particular concentration that will derive the initial values of these components of that reaction to a point of equilibrium. And this value is actually very small. So now, how do you examine if either we're going to accept this value or if we're not going to accept the value? Meaning that there's a point where we're going to neglect it or where we're going to have it. Because if we did go ahead here, we'd say this is x times 1 going to give us x, then this is x squared. We're going to have quadratic equations and all. But we want to avoid the quadratic equations because we know that the value of x is very small and it can be very negligible. What do? I will get to neglect the value of x, where I'm going to have x being equal to what? Let me find out. This is 1.0. I've neglected the value of x there, neglected the value of x there. I've only remained with 1.0. I'll divide. This has been neglected. This is 1.0. Then I'm going to multiply this 1.0 divide 1.0 by the 7.2, which is the value of Ka. 7.2 times 10 to the power negative 4. The value I'm going to have is what? 1 divide 1 is just a 1 times 10, 7 times 2 times 10 to the power negative 4 is the same as 7.2 times 10 to the power negative 4. So what I'm going to do here is I'm going to compare this value to 1.0. So since x is smaller compared to 1.0, it means that it is acceptable. And what we're simply going to do here is we're going to ignore it. Okay? We're going to ignore the x. All right? So now, what does this tell us? It tells us to say that when you come and find out what this expression is to find out the value of x, the value of x simply turns out to be 7 over 2 times 10 to the power negative 14, because we're saying that the value of x in this particular point is negligible. So we don't have to put up the quadratic equations and all. So therefore, this just becomes 1.0 divide 1.0 times 10 times 1.2 times 10 to the power negative 4. So this simply becomes the value of x. All right. So now you have the value of x as such, and then the question was asking you to find the percentage composition. Okay. So when you get back to the question was asking you to find out what is the percent dissociation of HF in a solution containing 1.0 molar HF. So now we know that the equation which has been given here is HF giving us the components what? The hydrogen ions plus that value there. So to find out what is this basic composition of this, okay? So now if the value of x is 7.2 times 10 to the power negative 4, what does this entail? It means that even here, the value of x is 7.2 times 10 to the power negative 4, and then on the other end here, it is going to be um, 1.0, and the value of x is 7.2 times 10 to the power negative 4. On the other end, we're going to have 1 minus 7.2 times 10 to the power negative 4. So we have all these values that are there. So this becomes, if you evaluate that, they become the concentrations of the HF at equilibrium, the concentrations of the fluoride ion at equilibrium, and also the concentration of the H plus at equilibrium. So therefore, that is what we're talking about. So now, to find out the percent of this in that, so we're just going to say, what is this divide this going to give us? So this is going to be multiplied by 100, because I'm trying to find out what is the percent dissociation of the hydrogen ions in the HF. And we found out the value of the H plus there. Okay? And the value of the H plus, we found out what was the concentration. It was 7.2 times 10 to the power negative 4. Divide the HF, which is just 1.0. You multiply that by 100. And when you multiply by 100, what you're simply going to have there is 0.072% as the percent dissociation of the hydrogen ions in the hydrogen fluoride ions. So simply this is how you get to work the question out. But what are some of the most important points we need to take from this? The values, and how you evaluate the values of x when you're dealing with the I stable. So you find out the initial concentrations on the side of the reactants they reduce. So that is a 1.0 minus x, 1.0 plus x on the side of the product, because you get to form more of the products. So guys, these are some of the basics I wanted us to know regarding chemical equilibrium or acid base equilibrium. Looking forward to be with you in the second part of the session. This has been Pomboroka. Thank you so much.